Hey everyone, welcome to The Explainer. Today we're exploring a really cutting-edge approach to one of the most pressing technological challenges of our time. And that is, how exactly do we secure complex AI networks? To really wrap our heads around this, we're going to use a fascinating lens. We're looking at George Mason University's CYSE 587 capstone project from fall 2026. This course is incredible because it literally throws graduate students right into the deep end of cybersecurity, demanding they think not just as coders, but as holistic systems engineers. Okay, let's take a quick look at our agenda for today. We are going to start with the modern AI network threat, define what systems engineering actually is, dive into the ADOP case study, unpack how to engineer trust, and finally, look at how to pitch that value proposition to leadership. All right, Section 1, the modern AI network threat. And we really have to act with urgency here because autonomous systems are deploying way faster than traditional security can keep up. So think about this for a second. How do you secure an autonomous AI? It's the exact high-stakes problem that engineering leadership is facing right now. Look, giving an AI agent the ability to read files, fetch external data, and write code, well, it's kind of like giving an eager toddler a blowtorch. How do you make absolutely sure it doesn't accidentally or maliciously burn the whole house down? To really understand the stakes, we just need to look at some real-world vulnerabilities detailed in the course material. Back in December 2025, major flaws were disclosed in Anthropic's reference Git server for the Model Context Protocol, or MCP. We are talking about massive flaws here. For example, CVE 2025-68143 had a severity score of 8.8 due to path validation bypasses. Then there was an 8.1 for argument injection. In plain English, this means an attacker could trick the AI into running malicious commands and completely taking over the server. When you chain these together, it creates a massive risk: remote code execution. This establishes the immediate, severe pain point. These AI tools that are meant to speed up development can actually open up catastrophic doorways right into your network. And the mechanism of attack here is just fascinating. It's a concept called indirect prompt injection. See, an AI agent doesn't need a hacker sitting at a keyboard typing malicious commands into a chat window. No way. The agent simply goes out to do its job, let's say fetching a seemingly harmless but maliciously crafted README file from an external source. It processes that untrusted content as context, gets totally hijacked by the poisoned instructions, and executes an attack. All of this happens without any direct human interaction whatsoever. Moving right along to Section 2, what is systems engineering? This is the holistic framework we need to combat these complex, cascading failures. The George Mason University syllabus defines cybersecurity systems engineering perfectly. It states that it's about the core principles for the design and management of resilient and robust systems throughout their complete life cycle. Now notice the emphasis on life cycle there. This isn't just about spotting a bug in a single line of code. It is about taking a huge step back and managing the entire lifespan of the system, really understanding how every single piece interacts from the moment it's deployed to the moment it's retired. When you compare the two approaches, the difference is night and day. On one hand, you have traditional reactive software security, which is what we usually see, right? You wait for a vulnerability to be disclosed, you panic a little bit, and you issue a patch. It's whack-a-mole. Proactive systems engineering looks entirely different. It requires continuous lifecycle assurance, rigorous risk reasoning, and a deep understanding of socio-technical boundaries. You aren't just fixing the engine when it breaks. You are engineering the entire car from the ground up to safely handle a blowout at highway speeds. Which brings us to Section 3, the ADOP case study. To actually teach these concepts, the students are given a highly realistic testing ground. That testing ground is known as the Agentic Development and Operations Platform, or ADOP. It's essentially an interconnected network of servers built on that Model Context Protocol we mentioned earlier. The AI agent acts as the reasoning engine and has to talk to four key servers: the file system, which holds the workspace; Git, which handles the version control; Fetch, for grabbing external context; and Memory, for maintaining knowledge across different sessions. To do its job, the AI has to constantly interact across these boundaries, and that creates a highly complex and inherently vulnerable ecosystem. And this leads us to a really crucial quote from the source material. The system is a socio-technical system of systems, not just a software application. You simply cannot secure this network by just staring at the AI model. You have to consider the big picture: the human engineers submitting tasks, the external networks providing the data, the logging systems, the CI/CD pipelines. They are all tightly interdependent. A failure at any one of these interfaces can spread like wildfire and cause massive organizational harm. Okay, Section 4, Engineering Trust and Assurance. So how exactly do the students engineer solutions for this incredibly complex system? Well, the course structures the solution through three major deliverables, which forms this really brilliant mini-narrative. By week 5, students must frame the problem and threat model, identifying the exact pain points. By week 10, they build a risk-justified architecture where they explicitly map their technical design back to those exact threats. And then by week 13, they finalize a value proposition package. This adds privacy, governance, and a cohesive business narrative. So they aren't just building a neat tool, they're building a highly defensible case for why that tool actually matters to a business. Now, all of this builds up to their ultimate challenge, which is governed by one very strict rule. The students absolutely cannot alter the agent host's core reasoning or the internal MCP code. And this is brilliant because it perfectly mimics reality. In the real world, you rarely get to just rewrite an external vendor's foundational AI model. Instead, the students are forced to observe the system from the outside. They have to rely on logs, Git histories, and external interfaces to engineer holistic oversight and governance tools. So, what do these external governance solutions look like in practice? Let's take 2 examples. First, an agent action risk monitoring tool. This essentially monitors the logs for excessive agency, making sure the AI isn't doing things it shouldn't, which provides a really solid defensible audit trail for regulators. The second is a tool output provenance tool. This one specifically scores data fetched from the outside to block those indirect prompt injections we talked about. It serves as an auditable gating mechanism. Notice how both of these solve the security problem without ever once touching the underlying AI model's code. Finally, we reach Section 5, pitching the value proposition. Because in systems engineering, having the best technical solution in the world is completely useless if you can't convince leadership to actually adopt it. To bridge that gap, the students use something called the Cybersecurity Canvas. Now, this isn't your standard business model focusing on profit margins. It's specifically designed to identify stakeholder pain, things like cyber threats and operational failures, and map the engineering architecture directly to solving those exact threats. It forces the students to prove exactly how their technical assurance reduces real organizational cost and liability. It takes that highly complex, raw engineering data and synthesizes it into undeniable business logic. And the whole course culminates in this, the Shark Tank Final. In week 16, the students have to completely adopt an entrepreneurial mindset. They step in front of a panel of technical investors, venture capitalists, and industry experts. They get exactly 20 minutes to deliver a live pitch and a working proof of concept demo. They have to defend their system's value, proving beyond a shadow of a doubt that their engineering choices actually solve the high-stakes security gaps without breaking the organization's workflow. It is the absolute ultimate test of their systems engineering capabilities. As we wrap up, I want to leave you with this somewhat provocative question to think about. Are you treating your network security as a simple IT problem or a comprehensive systems engineering challenge? As this GMU capstone clearly shows us, when you're dealing with highly autonomous, deeply interconnected AI tools, simply patching bugs just isn't going to cut it anymore. You have to secure the entire socio-technical system. You have to engineer trust. Thank you so much for joining me on this explainer, and I hope this completely changes how you look at the future of network security.